Welcome back for trig and pre-calc students. This is the third of 4 videos I'm making to talk about different ways in which we use the sum and difference identities. Now remember, the sum and difference identities are these. Okay, and one of the ways we actually looked at in video 1 was a complete the identity problem. And I said these were not my favorite, because I think they're a little bit ambiguous at times, or I think that's not necessarily the best way to ask what they're asking maybe. These are problems that are trying to help you get ready to prove or verify identities. They're just saying, how can I simplify this? How can I apply a property and break this down? Because technically completing it, an identity is just a statement that's true, and it's always true regardless of what these two values are. These are variables. There are a lot of things I could say over here that would always be true. But what they're wanting me to do is actually go ahead and apply the specific properties that are very directly applicable to this case. Now, let me point out, speaking of variables, these two variables are just Greek letters. This is no different than if it said x plus y, x minus y, or if it said a plus b, a minus b. In fact, that is what it says. Those are the Greek letters alpha and beta. Okay, so they're just saying we're putting variables in place of our angles. You don't know what the angles are. Now, I have a cosine with a plus, and I got a cosine with a minus. So that means I'm going to use both of these rules, the one with the plus and the one with the minus. So this becomes cosine alpha, cosine beta, minus sine alpha, sine beta. And this becomes, that would be a better way to do it, cosine alpha, cosine beta, plus sine alpha, sine beta. All right, so now the question is, can I simplify that at all? And the answer is yes. This term and this term are opposites of each other, so those are going to add to 0. They'll go away. Sometimes we say cancel. That's not technically canceling, but it's the same idea. Goes away. These two are identical to each other, and when you add two things that are identical, you just get 2 of that thing. So basically, that's as simple as I can get this, and that's where they want me to go. And I like to use these two little things. Sometimes people call them railroad tracks. That basically is just one of several ways mathematicians say, I'm done. I've gotten where I needed to go. I'm finished. Another way, sometimes people put a check mark or a smiley face. Another way is to write the letters QED, which means basically, I have shown it. I have shown that it is true. Quod erat demonstratum. Don't criticize my, or don't critique my Latin pronunciation. I am not a Latin teacher. But it basically means it has been demonstrated. I have shown what I needed to show. All right, another type of problem, a little bit more straightforward, is one like this. Find the exact value of the expression. Now, what you have to do on these is basically just recognize that the formula is in front of you. In other words, look at this and go, hey, that looks familiar. It looks like one of these. And then realize, yeah, it looks just like one of those. It looks like the very first one, but it looks like the right-hand side, not the left-hand side. So this is sine of some number times cosine of a different number, plus the cosine of the first number times the sine of the second number. That's the same thing. It's basically just, this is my A, this is my B. And so they're asking me, instead of going from here to here, I'm starting over here and going to here. So in other words, I can put these together and say that's sine of A plus B. So this is equal to sine of A plus B, which is 25 plus 35, and that is 60. Now, we happen to know the sine of 60 because that is a unit circle value. On the unit circle, 60 is right here. It's a 30, 60, 90 triangle. You go out 1/2 and up. Square root of 3 over 2. 1/2 root 3 over 2. The first coordinate's the cosine, and the second one is the sine. So the sine of 60 degrees, which is the same as pi over 3, is square root of 3 over 2. That's the exact value. Remember that exact value always means don't give me decimals. Okay, that's what it always means. It means simplify radicals if you have to, simplify fractions, don't change it to decimals. All right, here's another one just like that, where again, it's really that we just have to recognize that, hey, that looks a lot like one of those formulas, but I have to figure out which one it is and go from right to left instead of left to right. So sine times cosine, it's clearly one of the sine ones, and it's got a minus in the middle, so it's this one. So here's my A, here's my B, A, B, and my answer is going to be, that's the same, they've given me this side, that's the same as sine of A minus B. So that's the same as sine of 250 minus 10. 250 minus 10 is 240. 240 is a unit circle value. It's down here, 60 degrees below the x-axis, below 180. It's also 4 pi over 3. And that's going to be left 1/2. It's a 30, 60, 90 triangle. Down square root of 3 over 2. So there's my point. This is the cosine. This is the sine. They asked me for the sine, so my answer is negative root 3 over 2. All right, now we're starting to get into a little bit more fun. Once I figure out where I put the problem. Here we go. Use the given information to find the exact value of the expression. All right, now, the key thing to me, and the thing they're asking me to find is right here, but this is the info they've given me. The key thing to me here is this. They have told me what quadrant I need to work in. Anytime they tell you what quadrant, well, let me say this wrong. I don't want to say this incorrectly. Most of the time, there's only one reason for them to tell you what quadrant you're working in. And that is because you're going to need to draw a triangle in that quadrant. So that's a big clue. When they tell you what quadrant you're working in, that's a big clue that this is going to be a problem where I draw my own triangle. Okay? And basically, when you're drawing your own triangle, you start by drawing a segment that goes from 0, 0 out into whatever quadrant. So here, first quadrant, I'm going to draw a segment that goes from 0, 0 out into the first quadrant. Doesn't really matter where, just put it somewhere in the middle. And then go from the end of that segment back to the x-axis. And there's my triangle. Okay, so this is, variable is alpha. So my first angle I'm looking at is alpha. So alpha lies in quadrant 1. And they tell me that sine is 21 over 29. This is where you have to remember SOHCAHTOA. Back from when you first learned this, back in geometry, algebra 2, wherever. The sine, the definition of the sine is the opposite side over the hypotenuse. So if they told me that my sine is 21 over 29, that's the same as telling me this is the opposite side and this is the hypotenuse. So the opposite side is 21, opposite across from alpha, and the hypotenuse is 29. Okay, now there's only one side of that triangle I don't know now, and so I'm going to use the Pythagorean theorem to find that missing side. So, excuse me, let me turn on my calculator here. 29 squared, I should know this, I know. I'm a terrible person. Oh, yes, I should. It's 20. Whew, now I am embarrassed. I was just kind of saying it before, but now I'm embarrassed. But that's all right. I'm not embarrassed. You shouldn't necessarily know it. I'm embarrassed because I'm a math teacher. Math teachers should know it. Yeah. Anywho, the point is we have to find the missing side. And now I can find the sine, the cosine, or the tangent of alpha, or if I wanted to, the secant, cosecant, or cotangent, just by doing whatever side over whatever side, SOHCAHTOA. All right. Same thing goes for beta. I need to figure out what all these missing side lengths would be for beta. And again, they told me that beta lies in quadrant 1, so I'm going to draw beta in quadrant 1, draw a segment that goes into quadrant 1, go back from the end to the x-axis, There is my right triangle. Cosine from this part right here, cosine is adjacent over hypotenuse. Adjacent over hypotenuse, that means 5 is the adjacent and 13 is the hypotenuse. So 5 is here, 13 is here, and then I have to find, I have to find the missing side right here. Pythagorean theorem, 5 squared plus missing side squared equals 13 squared. When I subtract, I will get that this is 12. So now I can find whatever I need to find there. Since we're only using sine and cosine and the formulas for all these sums and differences, if you look at the ones for sine and cosine, they only involve sine and cosine. We really only need to know the sine and cosine for each of these. So for alpha, the sine we already knew was 21 over 29, but we can still see it on this picture. And the cosine is adjacent over hypotenuse, so that's 20 over 29. This angle was beta. For beta, the sine is opposite over hypotenuse, that's 12 over 13. And the cosine is adjacent over hypotenuse, which is 5 over 13. This is kind of a long problem, I know, because now we have to do what they actually asked for. Everything we've been doing so far was just getting the information we need, in order to do this. Because in order to do this, sum, cosine, that's this right here, I need to know the cosine of the angle, the cosine of the other angle, the sine of one angle, and the sine of the other angle. So that's what I'm ready to do now. So I'm going to take this and I'm going to write it down here. Kind of zoomed in a little bit too far, sorry. Too far for you to see this very well. But according to my sum and difference identity, this is going to be cosine of alpha, cosine of beta, minus sine of alpha, sine of beta, and we just found all that information right here and here. So cosine of alpha, 20 over 29, times cosine of beta, 5 over 13, minus sine of alpha, 21 over 29, times sine of beta is 12 over 13. All right, so now I get to multiply 29 times 13 for my denominator. This is not one I would expect myself to know off the top of my head. That's 377. 20 times 5 is 100. 21 times 12, 252. And when we add and subtract fractions, remember we get our common denominator. And then we add or subtract the numerator, basically, and that's what changes. Once we have a common denominator, it does not change. And there's my answer. It's not necessarily a pretty answer, but it's the right one. That's what we're supposed to do. Now, before we go on to another problem like this, I want to talk to you about the original problem. And remember, we said that this part that's underlined in squiggly orange tells me where to draw my triangle. So when I see that, I know I'm going to have to draw a triangle. And I'm going to have to find the missing sides of my triangle, and etc. Here's the thing. That's not the only way they could tell me where to draw my triangle. There are several different ways they could tell me where to draw my triangle. And it's basically saying there's several different ways they can tell you, they can name a quadrant. Another way I could have named quadrant 1 is I could say this. I could say that alpha is between 0 and pi over 2. Remember, pi over 2 is 90 degrees. It's the same place. So I could have said it in degrees. I could have said that. That's another way to say quadrant 1. Another way I could have said it's in quadrant 1 is I could have said the cosine for alpha is positive. That's what that's saying. Cosine is positive. The reason that matters is if I know that the sine is positive because they gave me a positive number here, and the cosine is positive, that tells me which quadrant I'm in. Because the sine and cosine are only both positive in the first quadrant. Remember that In your first quadrant, all sine, cosine, tangent, and their reciprocals, all of these are positive. Okay, in your second quadrant here, the cosine is now negative. So if you have a negative cosine, you might be over here. Cosine's also negative here. And the cosine is positive here. Remember, the cosine is like your x-coordinate. So x-coordinates are negative to the left and positive to the right. What about sine? Sine is like your y-coordinate. Y-coordinates are positive on top and negative in the bottom. So the sine would be positive here, and the sine would be negative down here. What about tangent? Well, the tangent is equal to, don't forget this, tangent is the same as the sine divided by the cosine. So that means if the sine and the cosine are both positive, so is the tangent. If the sine and the cosine are both negative, the tangent is positive, because if they're the same sign, if you have a positive over a positive or a negative over a negative, tangent's going to be positive. So tangent is positive here and in the first quadrant, and negative in the other two quadrants. So that's another way to tell us what quadrant to draw our little triangle in, our right triangle in, is to give us information that hints at what quadrant we're in. One more thing I wanted to point out to you. Whenever you are drawing a triangle like this, it did not come into play in this particular problem, because in this particular problem, they gave me sine and cosine values. Everything happened in the first quadrant. Everything was positive. If you are in any of the other quadrants, something could be negative. But when you're putting things on here, when you're filling in sides of your triangle, the hypotenuse, always make it positive. Always. So for instance, if they told me that I was going to draw a triangle in the second quadrant, and for instance, let's say it said the sine of your angle is going to be, that's not, why did I pick sine? That's a really good question. Let's say the cosine. Cosine of your angle is going to be negative square root of 3 over 2. Woo, can't see it anyway, sorry. All right, if they told me that I had a negative cosine here, and we say, okay, cosine's adjacent over hypotenuse, thinking of SOHCAHTOA, then here's adjacent, here's hypotenuse. All right, then this is the best answer. This is the best example. That one, I think you probably would have done that regardless. Let me give you a different one. How about if, here we go, tangent is negative 4/3 and it's in the second quadrant. Okay. I know you're thinking, where are you going with this? What I want to point out to you is that when you have a fraction and it's negative, okay, negative 4/3 could mean negative 4 over positive 3 or positive 4 over negative 3. All of those just mean negative 4/3. And I just realized I still just gave you a really bad example. I'm going to have to see if I can trim this video because I'm giving bad examples. All right, let's suppose I can't trim it. I'm going to sign out, tell you later. Sorry, later. Nothing I'm writing here is wrong. It's just not making the point I want to make. So you can just disregard the last 1.5 to 2 minutes of this video. But hopefully I can trim it for you. Sorry about that.